We are going to continue our discussion of gases by talking about molar volume. In your textbook, it's pages 135 to 137. By the end of this lecture, you'll be able to explain the concept of the molar volume of a gas, and you'll be able to perform multi-step calculations using a variety of concepts, including the concept of molar volume and the combined gas law. So the molar volume of a gas states that regardless of the type of gas you're looking at, 1 mole of gas at STP has a volume of 22.4 liters. 1 mole of gas at SATP has a volume of 24.8 liters. So what this means is it doesn't matter which gas you're looking at, and this is an extension of Avogadro's law. The volume that gas takes up is a constant. And what this does is it allows us to relate volume through molar volume, because molar volume has units of liters per mole, and it allows us to relate that to mass using our molar mass formula. Molar mass is equal to mass over moles, and since both of these formulas, or both of these formulas use the mole, we can relate mass to volume when we talk about gases. So here's just a list of constants for STP and SATP showing molar volume. Note that in your data book, these constants here are not shown, not in your data booklet. So if you're going to use them on a test, you have to do so from memory. The rest of the information is in your data booklet. And here's an example. So a sample of chlorine gas weighs 1.31 grams. We're going to calculate the volume of this sample at a different pressure and a different temperature. So what we're going to do is, since we have a mass, we're going to take that mass and we can convert it to a volume. Since we're looking for volume, we have to convert it to a volume. Now, using molar volume, we can get the volume at SATP or STP. I'm going to choose STP just out of habit. Once we have the volume at STP, we can find the volume at 3.2 atmospheres and 0 degrees Celsius. And we can do this using our combined gas law. So those are the steps we're going to take. So we have a mass, we have to convert it into a volume. Before we can do that, we have to get number of moles. So we're going to find out the number of moles of chlorine gas using our molar mass formula. We know that the number of moles is going to be mass over molar mass. It's the number of moles of chlorine gas. Notice that chlorine is diatomic, so we have to take the molar mass of chlorine and multiply it by 2 from our data table. So the mass was 1.31 grams, and the molar mass is 35.45 times 2. And so we get 70.9. And when we do our calculation, we get 0.0185 moles. Now that we have the number of moles, we are going to get the volume at STP using our molar volume. So we know that we have, we want the volume of chlorine gas, which is going to be equal to the number of moles we have times 22.4 liters for every 1 mole. So for every 1 mole, we have 22.4 liters. We have a little bit less than 1 mole, so we're going to have a little bit less than 22.4 liters. So we find out that we have only 0.414 liters at STP. And now we know the amount of, or the volume of gas at STP, we can calculate the volume at SATP using our combined gas loss. So we know that V1 P1 T2 over V2 P2 T1 is kind of the version we like to use. We're looking for volume 2, so I'm going to scribble that one out, and there's the version of the formula that I'm going to use. So V2 is equal to V1 P1 T2 over P2 T1. And now it's just a matter of plugging in our numbers. And so our initial volume is 0.414 liters. Our initial pressure at STP is 1 atmosphere. We have to either do our calculations in atmospheres or in pascals. And since 1 atmosphere is the same as 101.325 kilopascals, it's a fairly easy conversion to do. Our temperature 2 is 0 degrees Celsius, which is 273.15 Kelvin. And we're going to divide that by our new pressure, which is 3.2 atmospheres. And again, 0 degrees Celsius, 273.15 Kelvin. Now our calculation gets a little bit easier because these two numbers cancel. So we're just going to take our volume and divide it by 3.2. And so our volume at 3.2 atmospheres and 0 degrees Celsius is 0.129 liters. And we're allowed 3 sig digs, so 129 milliliters. Either of these answers would be acceptable. This one would be more likely on a test in terms of the units that would be given on the test. So we'll try another one. Here we have a sample of nitrogen gas with a volume of 378 milliliters. Again, at STP, we want the mass of this sample of nitrogen gas. So we're looking for mass. So in order to get mass, we need the number of moles, and in order to get the number of moles, we can use molar volume. So we're going to go from our volume. When we use molar volume, we'll be able to get the number of moles. This is liters per mole. Once we get the number of moles, we can find the mass using molar mass formula. And so there's our steps. So if we have, and I'm going to convert it to liters, so right now we want the number of moles, so the N of N2 gas is equal to 0.378 liters. And now since we want our answer in moles, we're going to put our 22.4 liters on the bottom, 1 mole at the top, and so we're going to actually divide the 3.78 by 22.4. And we end up with 0.0169 moles. Once we have the number of moles, we can find the mass. That mass is equal to and I got this formula up here, I have it written down upside down, that's why I'm getting so confused. So hold on a second. Molar mass is grams per mole. We want to solve for mass, so the mass of N2 is equal to molar mass times the number of moles. Just multiply both sides by moles, and they cancel on the one side. The molar mass of nitrogen gas is 14.1 times 2 because it's diatomic. So 28.02 grams per mole times the number of moles, which is 0.0169 moles. And when I'm doing these calculations, I'm saving the full value on my calculator. So what I'm actually running through in this spot is the 0.16875. It's the full display on my calculator. I'm just rounding it off when I'm writing the calculation down to save some space and time. But I use the full value of my calculator. I don't do any rounding until I get to my final answer in terms of the calculations. And so my mass is 0.473 grams, which is the same as, and we have 3 sig dig, so 473 milligrams. Okay, so with this question, here we have an empty syringe with a mass of 1.2701 grams. When we fill it with pure oxygen, it has a mass of 1.2747 grams, and we fill it with 3.5 milliliters of gas. The pressure inside the syringe is 99.5 kilopascals, and the temperature is 22.5 degrees Celsius. We want to find the molar volume of oxygen. We know that the molar volume of oxygen should be 22.4 liters per mole at STP. So based on the information we have, we're going to find out if that is indeed the molar volume of our sample. So we have 3 things we need to do. The first thing we need to do is we need to find number of moles. We need to know how many moles we've actually trapped if we want to find out the molar volume. The other thing we need to find out is we have to find the volume at STP. And the last thing we're going to do is divide these 2 things out. We're going to divide our volume by the number of moles. When we do this, we should get close to 22.4 liters per mole. So those are the 3 steps we're going to do. So the first thing we're going to do is we're going to find the number of moles. Now we have a couple of things. We don't know the number of moles, but we do know the mass, because we can subtract the 2 masses of our syringe. The mass of O2 is 0.0046 grams when we just subtract our 1.2746 and our 1.2701. So we have the mass. We also know the molar mass of O2 is 32.00 grams per mole. So we can divide those 2 things out and we can find out the number of moles. We know that molar mass is equal to grams per mole, which means the number of moles of O2 is equal to mass divided by molar mass, which is 0.0046 grams divided by our 32.00 grams per mole. When we do that, we get 1.4375 times 10 to the negative 4 moles. So now we have the first part. We have the number of moles. The next thing we're going to do is we're going to find the volume at STP. We have a volume of 3.25 when the pressure is 99.5 kilopascals and the temperature is 22.5 plus our 273.15. So we're going to get 297.65 kelvins. So that's the first set of conditions. We can use our combined gas law to get our second set of conditions. So we're looking for volume 2, and we have a pressure of 101.325 kilopascals and a temperature of 273.15 kelvins. And so I'm a little short on space, so I'm just going to write in our variables here. It's going to be volume 1 times pressure 1 times our temperature. The two our 273, temperature 273.15, divided by our pressure 2 and our temperature 1, the 297.65. When we do that division, we get 1.438 times 10 to the negative 4. Oh, sorry, that's our number of moles. This is our volume. 3.17 milliliters. So this is just a continuation to give us some more space. We found our volume in the syringe, and we found the number of moles in the syringe, and so all we need to do is find our liters per mole, or we can find our molar volume is equal to our 3.1754 milliliters divided by 1.438 times 10 to the negative 4 moles. So 3.1. And the answer we get is 22.082 milliliters per mole. Notice we want units of liters per mole. So to get this into liters per mole, I'm just going to rewrite my equation here. 22.082 milliliters in 1 mole. We want an answer that has liters, so we're going to multiply this by a ratio that converts milliliters to liters. So in 1 liter there's 1,000 milliliters. When we do this, our milliliters cancel, and so what we're going to end up doing is dividing this number by 1,000, and we end up getting 22.1 liters per mole. So 22.1 liters per mole, that's very close to our 22.4 in chemistry or in science. When we're comparing a experimental result, so this would be the result from an experiment, we can compare it to our theoretical answer using something called percent error, and percent error is equal to your experimental value minus your theoretical value divided by the theory value. This we're going to take the absolute value of, so we always get a positive answer, times 100%. And so we'll just run that through and see how close we are. So the 22.1 minus 22.4 absolute value divided by 22.4 times 100%, and we get 1.3% or 1.33%. 1.34%. Generally speaking, error is less than 10%. So this is a good answer, or it's an acceptable answer. It's close enough to the theoretical to be assumed that so that we can assume the theoretical answer is right. So molar volume and molar mass, we can relate the two. Many gases are stored as liquids in order to save storage space and transportation space. We can think of propane. The propane you use under your barbecue is stored in a liquid inside that tank. As you use it to heat food on your barbecue, it's being vaporized into a gas. So that's one practical use of storing gases as liquids. And because of this, we can actually find out the amount of space a gas would take up given its mass as a liquid using our molar mass formula and our molar volume concept. So here we have an example of a propane tank holding 20 pounds of gas, your typical barbecue propane tank weighing 9.09 kilograms. We want to find the volume occupied by that gas at SATP. So the first thing we're going to do is we have a mass. We're going to convert that mass into moles. Once we find the number of moles, we're going to find the volume using our molar volume. So here we're going to use our molar mass formula. Here we're going to use our molar volume formula. So we'll start with our mass. So propane is C3H8, which means its molar mass is going to be 3 times carbon's molar mass plus 8 times hydrogen's molar mass. So the molar mass of propane is 44.11 grams per mole. We know that molar mass is equal to grams per mole, and we want to find the number of moles because we have the mass. So N of C3H8 is equal to mass over molar mass, and I'm going to convert my mass into grams, so I'm going to multiply it by 1,000. Multiply by 1,000. Here we go. 9090 grams divided by 44.11 grams per mole. And so we end up with 206 moles of C3H8, which is a lot. That's a lot of moles of gas. This is why they don't allow propane vehicles in parkades, because if there's a leak, that propane's heavier than air and it can fill a huge space. So in a 20-pound tank, now we can use the concept of molar volume. We want to find the volume of C3H8, and since it's at SATP, we're going to use our 24.8 liters per mole, our second constant. So the volume is going to be the 206 moles. We want an answer in liter, so we're going to be multiplying by liters, dividing by moles, times 24.8 liters over 1 mole. So our moles cancel, and we'll end up with an answer in liters. And this should make sense. If 1 mole takes up 24, or if 1 mole takes up 24.8 liters, then 206 moles would be 24.8 times 206. And so we get 5,010 and we'll go 0.7 here liters, and we're going to report it since we can only have 2 sig digs, or 3 sig digs, I guess, if we use our conversion. So we're going to keep 3 sig digs, so it's going to be, we'll go in kiloliters, 1, 2, 3, 5.1 kiloliters, which is a lot of space.